Okay, so welcome to week 3, class 1. I'm recording now for the people who have already joined me. Last week, we we started chapter 2, which is the big chapter. It's like 180 plus slides. And we started talking about properties of water. So density, viscosity, pH. Those are wink, 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 very good things to know. Tonight at midnight, you have a quiz on chapter 1 due. Very shortly, I will be posting another quiz on the beginning of chapter 2. Chapter 2 is so big. I'll have I'll have probably 2 quizzes, maybe 3, but I'm thinking probably 2 quizzes on chapter 2 because it's so big. If you can remember what we talked about on Thursday, or what I mentioned is if you had time to read slides 33 to I think slide 40, so I could quickly go over them today. The only reason I asked you to do that is because uh, it is an important concept, but it's about the United States, which none of us are living in right now. This is a Canadian course that's offered in the Middle East, and these are laws from the Environmental Protection Agency, the EPA, that's in the US. And I mentioned last week, I think the reason they did that is because, the US, all of this stuff is readily available. It's been available for decades online or through government agencies, so it's clear, it's easy to read, it's all there. Let me just double check that I'm sharing my PowerPoint, which I am, and I'll make this full. And I am going to go a little quick through these slides. You might have a question on this in the second quiz, but again, you'll have your notes with you. This, in my opinion, is not the most important thing in chapter 2. So I'll go a little quick, but don't skip this. Make sure, if I ask you a question on the EPA, it's around, slide 33. Oh, Nahala, okay, perfect, you're back. You changed your name. I will mark you in right now. Okay, cool. And to the people listening to this on YouTube, just ignore what I just said. Okay. So, EPA, Environmental Protection Agency, created by the federal government in the United States. Every country, certainly every developed country, any place in the Middle East I've seen, certainly Canada has their own version of an agency that looks after environmental issues or affairs. Things were changing back when I started creating this course. The ministry was reshuffling, but there, a lot of the links that I use later in this course or images and graphs were from the Ministry of Interior or the Ministry of Environment, MOE, which I think if you Google MOE now, you might get the Ministry of Education in Qatar. So still, the information is pretty much the same. So the EPA, a lot of the numbers that I'll be using in this chapter, parts per million, I'll talk about what that means a little bit later, but a lot of the standards come from the EPA, and different countries have very similar quality standards. So if you were in, Indonesia or Japan or here in the Middle East in Qatar, and you wanted to test drinking water, the water quality standards for, like, say, the amount of lead or arsenic allowed in that water would be similar. So water quality standards are provisions, kind of rules, I guess you could say, from states, territories, tribal, federal laws. Again, it depends on the country you're in, but in this case, we're talking about the EPA, and it describes the condition of a water body. So, it could be a lake, a river, a stream, the ocean even, or coastal areas, or the level of protection. So The EPA could talk about what type of protection they would give to a certain area. And part of, I shouldn't say part of me, but something there reminds me of the mangroves in Qatar, where they're typically protected. There's like cleanups to, to take the trash away from those protected areas. You think of like the sea turtles that come to the beaches here, they're all protected areas. They can also mandate or, again, provide rules on how the desired conditions will be expressed or established for future waters. So these standards could be the current condition of a water body, the level of protection that's going to be offered to that water body, no swimming, no boating, no dumping, or even a law that will explain how the water will be affected in the future. So I can give you a good example from where I'm from. In the early 90s, there was a cod shortage. We have codfish, so a white fish. You can kind of think of hamor, but a little different, cold North Atlantic fish. And in the early 90s, the amount of cod was getting drastically low. So the government put what they called a moratorium in, meaning basically nobody could fish. It was done. The whole industry ended. So no fishing, no commercial fishing at least, to try and replenish the stocks. So that was a mandate from the government to try and manage the condition for the future. And I mean, this is now 2020, so 30 years later, there's still, it's not what it used to be, but things have changed for the better, I think. It's been a long time since I looked at that, but that's just an example. So these standards are legal bases, I guess, in the United States, and the same in the Middle East. Here in Qatar, the Ministry of Interior or Environment would have laws, if you get in trouble for dumping something in the Corniche, for example. All right, I'll go a little faster now because I just want to talk very quickly about these 4 things. And again, wink, wink. I know you can't see my face, but I might ask you, a matching question or fill in the blank for one of these 4 things. So water quality standards typically consist of 4 kind of areas. There's designated uses, criteria, anti-degradation, which kind of explains itself, but if you don't know what that word means, I will explain it, and then just general policies. So let's quickly look at these 4, and then I can move into something a little bit more interesting. Oh, sorry. Okay, so the first one, designated uses. A designated use would, for any object is like using the object for its purpose. So if you were in the kitchen, your designated use for your oven is to cook food. You don't dry your clothes in there, it's not or you don't. Yeah, I guess that's a good example. Your oven in your kitchen, it's for cooking food, not drying clothes. It has a designated use. So a good water quality standard would give a body of water a designated use. So is the water for wildlife, like the Great Barrier Reef or the mangroves? Is this body of water to be protected? Meaning, very little activity. Is this water for recreation? Is this for swimming, for boating? I was down a long time ago now. I haven't left in so long. But I was at the Pearl near the Grand Hyatt beaches, and there's, all sorts of boats, high-speed boats and Sea-Doos, and there's people swimming, watercraft and people. Obviously, that's for recreation. You don't drink that water. That water's not used to protect wildlife. It's for fun. So that's another designated use. Public drinking. Now, a little different in this country because the water here is desalinated from the ocean. But where I'm from, it's actually behind my parents' house. You can drive there in maybe 10 minutes. You could jump in and swim in the water that we drink. I think it's called Watson's Pond. Anyways, maybe not. And it doesn't matter what it's called. But the idea is that public drinking water is open. It's you can, put a boat in it. You could dump toxic chemicals in it if you wanted, but that's not its designated use. So in that water supply, I think it's fenced off and you can't swim. There's no boats. The only things that can really interact with that water would be animals. And I mentioned in an earlier class, that is another issue for illnesses. We'll talk about that later. Water kind of borne illnesses, but still, public drinking water is usually not open for recreation. Other water supplies could be used for farming, industrial, navigational, and other purposes. You can kind of be creative there, right? The designated use is kind of whatever the government wants. Farming or industry would be two big ones. Criteria. So again, I'm going through this list. This is criteria to protect. This is again from the United States, but every country has, their own criteria. The criteria, this is actually interesting, and this kind of speaks to science in general. Typically in science, a criteria can be a numerical criteria, like the mass, the volume, the density, or it can be a narrative. So like a descriptive word, like this chemical is clear and colorless. This chemical is blue and cloudy. Well, that's chemistry. In water quality, the criteria can be numeric. Typically, the numeric value is given in parts per million. Oh, this pen. It's not my pen, it's PowerPoint. I've used another pen. Okay, there you go, parts per million. We'll talk a little bit about that later. It could also be parts per billion too. But we'll talk a little, again, we will get into these numbers a little later. These numbers are typically found on government websites. So, I know the Canadian government would have these numbers there for acceptable criteria, acceptable levels of, say, lead in water. They can also be narrative. It can describe the conditions of the water. So, they might say this body of water should be free from all recreational activity. This body of water should be free from all industrial waste. I mean, that I guess should be every type of water, but you get the idea. It's not a numeric description. It's like a verbal description of what the water should be. So yeah, that's criteria. Anti-degradation requirements. So anti means like the opposite, or no. And degradation, hard word to say for me today, is kind of like loss in quality. So like to anti-degradate or to have anti-degradation requirements, these are requirements to keep the condition or keep the quality of the water the same or better. It's so it doesn't degrade in quality. That's kind of what I was trying to say there. You don't want the condition to get worse or degrade. So one of the principles in the Clean Water Act from the EPA is to maintain the chemical, physical, biological integrity or quality of the nation's waters. Now, obviously, this is America, USA, but every country has the same thing. Qatar, Canada, Japan, South Korea, like it doesn't matter. The government, a good government with an environmental conscience would have this type of statement in their environmental policy. You want to keep the chemical quality, physical quality, biological quality the same. You don't want things to get worse. So anti-degradation requirements give a framework, like a guideline for maintaining and protecting water quality, which is kind of where we come in. I say we, I'm a teacher. Where you guys might come in, your environmental health and safety people, the idea is any part of the environment, your goal typically is to maintain and protect as much as possible. Whew. Okay, last last one. General policies. This is just kind of the blanket statement that covers everything else. So there's policies and provisions, just like think about rules or laws that can talk about standard implementation, such as like a mixing zone, low flow policies. This is a big one in kind of talking about urban waste. You keep the flow of a water supply low enough, you're not going to degrade any of the environment around it. There could be a lot of runoff with high flow waste. So if you keep the flow low enough, you're not really going to disturb the environment around it. This is kind of like, again, if it doesn't fall into the first three categories, there's just other general policies. We will talk about, I know we'll talk about mixing and low flow policies a little later in this course, especially when we talk about something called turbidity. So this we'll talk a little bit about later. All right. That's boring. That's no fun. We'll get into section 2.2. Okay, I'm excited for this. This is perfect timing for our lab tomorrow. The last thing about this, guys, by the way, the EPA's like recommended criteria, sorry, is all online. It has a list of like 150 different pollutants, and you can look at the table here. Now, it says 2016, because I think the last time I taught this course was 2018. I think this list still exists in 2018, and I forgot to even look it up. Yeah, it's still here. That's why I wasn't really too nervous about it. Let me share my screen for 1 second. Now, guys, you obviously do not have to, memorize or understand or anything about these numbers. Oops. So there's aquatic life criteria table and human health criteria table. So completely different, but very much related. So let's look at the human health criteria table, and we can pick any chemical. Let's pick lead. Oh, my Google Chrome's not being fun. Oh well. It's in alphabetical order. LMNOP. Let's see if it's here. Oh, it's not here. Well, let's pick another chemical. Nickel. Nickel's here. So here's nickel. You can click on this for more information. There's some information about when this law was, put into effect and when this law was revised. And then these are the numbers. So nickel is 610. I just want to double check the column. So the acceptable human health, the acceptable level, this is micrograms per liter, so ppm. This was, what did I say, 610. This is human health for the consumption of the organism only. This is human health for the consumption of water plus the organism. So these are our ppm levels of safety. And you can kind of look at any chemical here. Arsenic, you can see the level is extremely small for acceptable levels. We're talking 0.018. Some are way more acceptable. Like, I don't know if calcium is here. Oh, I thought I saw magnesium, but it might have been manganese. No, magnesium's not here. I don't think they're kind of classified as dangerous to human health anyways. But let's look at another one. Well, they have the pH here, 5 to 9. Phenols, they take 4,000. Selenium, 170. Toluene, it's an industrial solvent, 57. So anyways, you get the idea. This is a list. And it's actually kind of interesting. I've compared this list to the list of the local government, like the Qatari government, the Ministry of Environment or Interior. This was a few years ago now when I compared all these lists. And they're kind of different. It's kind of weird. They're not as much different, that I would be worried, but the numbers are not the same. So it's, wherever you guys go to work, it could be in the Middle East, it could be in, the UK, it could be in Canada, I don't know. These numbers won't always be exactly the same. It's totally dependent on the government. All right, I mean, guys, that was not the most interesting stuff I know. Personally, not for me. It's not my type of stuff. I very little to do with chemistry, so it's not my uh, favorite area. But just make sure you kind of even know what these words mean here on this slide. Okay, so designated uses, what's the water used for? Criteria to protect. So what are the criteria? What are the numbers and descriptions that we want to have this water? 1,000 ppm, 10 ppm. Do we want to keep it free from boats, free from humans? What do we want to do? Requirements to keep the quality the same, and then there's other general policies to kind of address any other issues besides those three. All right, boom, my favorite part. We're getting into the chemistry now. Section 2.2. This is the environmental chemistry part of all this. Section 1 definitely had some chemistry in there, but this is now we're going to start really talking about the chemistry of the water, and this is really good place to be for our lab tomorrow, because our lab tomorrow is about dissolved oxygen. So I have with me, I won't put myself on camera now, but I have with me this big black box, this big briefcase is what it looks like, or suitcase, and it's full of test equipment. So tomorrow afternoon, don't hold me on the 2 p.m. because I am going to make a video and I kind of edit it and take different takes or recordings. But tomorrow afternoon, sometime around 2 or 3 p.m., I will upload that video with the lab. And in that video, I'll show you the kit. Kit, K-I-T. So, like a little, I don't know, a box of things to do. It's almost like activities, but it's science. So in that kit, there's like dissolved oxygen tests, there's pH tests, nitrate test, what else is there? Phosphates. There's a few other tests in that kit. And we're going to do at least 4 of those tests. And the first, like I said, is dissolved oxygen. So I will have that lab video up tomorrow around 2 or 3 p.m. Again, give me some time to edit it so it's not too crazy. So this is a good thing to do. I don't think I'll finish this section today. I might. But this is really good. We're going to talk about dissolved oxygen. So I'm going to define it, explain why it's important, explain how industrial activities affect it, state how temperature affects it, and then state the units for measuring dissolved oxygen. All really, really important. All right, let's get started. Oh, and acceptable levels, kind of like what I just talked about on the previous slide I was showing you. Am I showing you my I'm not even showing you guys my PowerPoint. No one said anything. Sorry. I'm just rambling with the EPA page open. I have this here. So yeah, these are the outcomes we're going to cover in this section. The last one, or the second last one, is actually a question I typically ask on a quiz, is to explain why the maximum level of oxygen that's dissolved at 20 degrees Celsius is 9 ppm. And then we'll talk about measuring dissolved oxygen. So, okay, let's get started. The definition. It's literally exactly what it is. It sounds like. What is dissolved oxygen? It is O2, oxygen, or just O, but when we say oxygen in the environment, we typically mean O2 that has been dissolved. There we go. Okay. Now, dissolved oxygen is the free non-compound oxygen present in water or other liquids. Now, very important thing to remember from Chemistry 1200. We call O2 a molecular element. Okay, so you might think, and you're not really wrong. I think if you if you look this up with, if you know, brought this up to an English major, they might have questions for you. But you might be thinking, wait a minute, you know, O2, that's a compound. A compound is two or more elements bonded together. And yes, you're right. But O2 or oxygen, you know, how we breathe this is, you know, such a, it's a molecular element. It's the molecule is so prevalent in this state, and it's such an important chemical in this state that we call it a molecular element. So when I'm saying measuring dissolved oxygen, I'm not talking about the oxygen in the H2O, right? You know, water, I'm not talking about that oxygen. I literally mean O2. In the study of lakes, limnology, I think I'm saying that right, dissolved oxygen is the most essential factor after the actual water itself. So big star here. When you're studying lakes, you know, so freshwater lakes that have a lot of marine life in it, the dissolved oxygen level is like one of the first things you would test. A dissolved oxygen level that's too high or too low can affect water quality and really harm aquatic life. So, you know, your fishes and plants and animals, I guess I could easily say. If any of you have a aquarium in your home, and you know, in a good aquarium, I don't mean like an old fish bowl, but I mean an aquarium, there's typically like a water pump and like water being mixed and circulated in. Um, there's parts of the aquarium that help pump in or keep oxygen in that water. I'm not a biologist, so I can't confirm this is true, but I remember when I was really young, I had a betta fish, which are, you know, very easy pets, kind of goldfish-like. Uh, and I had him in a fish bowl, and he didn't live. And I think I had two, and I just couldn't keep them alive. And the guy at the fish store said, I should get like a real tank with a pump and a filter, and you know, all the equipment. My mom was like, no way, you know, I'm not spending all this money on a fish. So especially when we had a cat, I think one of the fish my cat ate, it wasn't the water. Long story short, I don't think the bowl was, it worked very well. I don't think the fish had enough dissolved oxygen. I mean, I fed it every day, but there was some reason it didn't survive. So could have been anything. It could have been temperature, but young scientist me, thought it might have been the oxygen because the guy at the fish store said I needed a water pump thing. Anyways, so dissolved oxygen is non-compound oxygen, free oxygen, O2, and it's not bonded to anything else, so water doesn't count. And I just got a little picture of oxygen there. If you remember Lewis diagrams, oxygen looks like this. Okay, so it doesn't matter. We're not going to talk about Lewis here, but it is nonpolar. If that matters for anything to you, doesn't really affect anything that we were talking about earlier when we talk about the polarity of water. But there it is. There's oxygen. So I just have a picture here. There's these pictures I have. They're about the best quality I can get from the source I'm using, and I have the source linked later. There's an amazing website where a lot of information from this course can be found, but they have this picture, and you can see like the hydrogen. First of all, you can see the hydrogen bonding here. Okay, and these are not part of dissolved oxygen. We are typically measuring this. And in tomorrow's lab, we're going to measure the dissolved oxygen in my water. I don't think I'm going to get to anywhere special. I might be able to get some from a swimming pool or my tap water, but tomorrow we're going to measure the dissolved oxygen in Qatar's tap water, which is typically what we do in the lab anyways. But we also test the dissolved oxygen in the fountain outside the chemistry or engineering building as well. But I won't get to do that. So dissolved oxygen can enter the water two ways. This is Definitely good to know. Wink, wink. Yeah. Oh, and I guess I should mention, where does the water come from? Right. So, or not water. Sorry, I'm tired. Where does the oxygen come from? How does it get into the water? So there's two ways. It can enter from the air, and we call this process diffusion. So obviously, the atmosphere around us is full of gases like nitrogen and oxygen. Well, some of that oxygen just naturally dissolves in the water. Water is a solvent that can dissolve this O2. So diffusion, meaning the gas oxygen in the air gets dissolved in the water below. You can see some other processes in the water. We'll talk about this later. Well, okay, no, I shouldn't cross those out. We'll talk about these processes a little more later, but photosynthesis and wind cycling help create more dissolved oxygen or mix the dissolved oxygen in better. So this air, right, diffusion from the air, or photosynthesis, you guys know a product of photosynthesis is oxygen and water, but just oxygen. That would be your plant byproduct. And through waves in the wind, this oxygen is cycled all throughout the water. So it doesn't just stay at the top, it gets circled through like a giant mixer. Okay, I have a better picture here of the process of photosynthesis, which you guys would have learned in high school or middle school. You certainly learned if you did biology here. So dissolved oxygen can be diffused from the air above the water or created with the plants in the water through photosynthesis. And again, if you can't remember photosynthesis, it takes carbon dioxide and sunlight, and we get oxygen as a byproduct. All right, so wink, wink, wink. You will see this again. You definitely need to know this. How does dissolved oxygen get in the water? It is from the atmosphere and a plant byproduct. And I just have these pictures made a little bigger. You can see they're a little blurry. All right. This is the best quality I could get from that site. I'm surprised the link isn't at the bottom, but it should be. I just changed all my slides to widescreen, so I lost a couple things, and I'm editing them now as we go. But anyways, I will have that link for you for this site very shortly. Okay, guys, so it's been about an hour. It's 11:25. I'm super sorry. I know this can be a little boring. I just want to see where I want to get. Okay, I'm not going to finish this today, but that's okay because I can do the lab on Wednesday, and then we can kind of finish up this concept of dissolved oxygen on Thursday. So let me talk about plant life. And well, basically let me do 4 more slides and I'm done. All right. And that'll kind of get us ready for the lab tomorrow. And then I'll kind of finish this up a little bit later. There is an experiment we're going to do, or I'm going to try in my kitchen, where I look at the effect of temperature on dissolved oxygen. And I'm literally going to use my stove to heat up water. I have a thermometer, but I don't have any of the fancy lab hot plates here, but that's okay. So 4 more slides, and then that'll be it for today. So dissolved oxygen is necessary to many forms of life. I mean, to fish, invertebrates, bacteria, plants in the water. Again, dissolved oxygen is one of the most important factors in a lake that an environmental scientist, somebody in, environmental health and safety, if they were going to study a parameter of the water, they might look at dissolved oxygen first. Organisms like the fish in the picture, for example, use oxygen in respiration just like us on land, but they don't breathe like we do by taking a breath and filling our lungs. Like take a fish, for example, they have gills. They breathe their oxygen through the water. The amount of dissolved oxygen that something needs varies. It's obviously not the same, kind of like the amount of oxygen for creatures on land. So your pet cat, the amount of oxygen, well, I mean, we all need a certain amount of oxygen to live, but, with different lung sizes or different amounts of oxygen to keep your metabolic rates going, it's different. for every animal. So maybe you and your cat was a bad idea, but like you and maybe an insect could very different just atmospheric oxygen needs. So fish and crustaceans get oxygen for respiration through the gills. Plant life and phytoplankton, we'll talk a lot about phytoplankton later, require dissolved oxygen for respiration when there is no light for photosynthesis. So there's a difference between the dissolved oxygen in water in the daytime and then in the nighttime. We'll talk about that a little bit later. That's really interesting. If we could test the dissolved oxygen in like a lake or pond in noon and then again at midnight, it would be slightly different. It should be slightly different, I should say. And then microbes such as bacteria and fungi use dissolved oxygen to decompose organic material. DO obviously means dissolved oxygen, not DO, it's dissolved oxygen. Okay, 2 more quick slides, and I'm going to get into like some crazy math here, but that doesn't really matter for you, and then we're done. So in a stable body of water with no stratification, that means like different levels, in just a stable body of water, dissolved, like again, stable. So like temperature is not changing, there's not heavy waves, we're not doing anything to it, like just a stable, controlled body of water. The dissolved oxygen will always remain at 100% air saturation. What I mean is, and this goes into if you guys did chemistry 1201 or 1210, it establishes an equilibrium. I don't know if you guys can remember that. If you can't, it kind of doesn't matter for this course. But it establishes an equilibrium, and the water, basically what I'm saying is the water, when stable, will hold as much gas as chemically or physically possible. It's based on equilibrium, which is controlled by temperature. Wink, wink, wink. We'll talk about temperature a little later. So all I'm saying is, if you have a body of water and it's just sitting there and we're not affecting it in any way, that water will chemically absorb as much oxygen as it can hold. That's how equilibrium works. We can change that number with things like temperature, which again, talking about the amount of dissolved oxygen in water in the daytime and nighttime, also related to temperature. Anyways, the number can be calculated for how much dissolved oxygen a sample can hold at 20 degrees Celsius at sea level. Now, my phone says it's 37 degrees Celsius right now, so I'd have to do a different calculation, but 20 degrees Celsius is kind of like the standard that they would use in science. Some places use 0, some places use 20. I'm picking 20 because it's more common in the environment. So this number comes from Henry's law. This is not in the course outcomes. You do not need to know Henry's law. And guys, on slide 54, you do not need to know these calculations, but they are cool to know. They're cool sunglasses, not regular glasses. Okay, so I put them there because it is cool to know where these numbers come from. They're not made up. These are actual numbers. This 2 rounds up to 3. My computer didn't show all the numbers there. So using Henry's law, which we're not going to get into, but it is a law. It is a physical and chemical equation. The amount of dissolved oxygen when it's fully saturated at sea level and 20 degrees Celsius is 9 ppm. Milligrams per liter means ppm. Now, I said earlier micrograms was ppm. That was ppb. Milligrams per liter is ppm. I misspoke there, sorry. So 9 ppm is the number we're looking for in typical water at around 20 degrees Celsius. If it's a little bit less and a little bit bigger than 9, it could really be based on the temperature, could be based on the water quality, things like that. But 9 is like our magic number here. So tomorrow, guys, I'm done now. Tomorrow, my apartment or the place I live is typically around 20 to 22 degrees Celsius. I like it a little cold. And tomorrow I'm going to test water. And we're going to use the test kit. They've all been kind of replaced. So I hope, a couple of years ago, they weren't in good condition, but we fixed them all up. And we're going to see tomorrow if the dissolved oxygen is around 9 p.m. And that will be our lab tomorrow. Okay. So this is a really good place to finish. I'll talk a little bit more, obviously, next day about dissolved oxygen, how we measure it, how temperature affects it, and things like that. But this is a great place to finish with this magic number of 9. That's our ideal number of dissolved oxygen at 20 degrees Celsius. I got the hiccups now. So I'm going to stop record. If you guys have any questions, let me know. And guys, specifically, if you have any questions regarding your assignment or lab, because your assignment is due tonight at midnight and your lab is due tomorrow at 2 p.m. Guys, please, if you need extra time, send me an email. And if you have any questions, let me know right now. So I'm going to hit stop record. If there's no questions, have a great day. And I'll see you Thursday in class, and you can check my lab video tomorrow afternoon. All right, goodbye.